Let's practice the Markovnikov's rule for the hydrohalogenations of the alkenes. This is going to be very important in the following sections of the alkenes reactions that we're going to do, and you do want to make sure that you understand how this works. So let's start from the first one. We have this unsymmetric alkene and we're adding the HBr. In all of these reactions, the first step is going to be the protonation of the double bond. So HBr is a source of proton, so we can visualize this as having an H+, and that's going to be the first step of the reaction. The electrons of the double bond are going to attack the proton, and you're going to have two possibilities here. One of them would be placing the hydrogen on this terminal site, and if we do that, now this is going to be positively charged. And the second possibility is if you put the H in the middle, and in that case, now this is going to be positively charged. Out of these two, the one that is more stable is going to be formed. So notice that this is a primary carbocation and this is a secondary carbocation. And if you remember, more substituted carbocations are more stable. So in this case, this secondary carbocation is going to be formed. That's why from here, you can in a way just discard this. This is not going to participate in the reaction. And so use the more substituted carbocation. Then now you're going to place the Br. So second part of this reaction is the Br, right? So here we have hydrobromic acid, and depending on the halogen, that's going to be the one that is attacking the carbon. So here we have the Br, and we can visualize this as being a nucleophile and attacking this secondary carbon. That leads us to this product. We'll have this, the Br in the middle, and we have the H on the side. To summarize this reaction a little bit, remember in the hydrohalogenation reactions of the alkenes and in many other reactions of the alkenes, the group, let's say the bromine here, is going to the more substituted carbon. So right from the beginning you can identify that, so that's the more substituted carbon, and that's called the Markovnikov's position. And the one that is less substituted is the anti-Markovnikov position. So the group then is going to go to the Markovnikov position because that goes to formation of the more stable carbocation. And that's essentially the Markovnikov's rule. Now let's do the next one. In this example, again, we have two positions on the double bond. So that's the less substituted position of the double bond. And this is the more substituted position of the double bond. And that means that the Cl is going to end up on this position. So we won't show the mechanism in this case. And what you can do is draw this out, the carbon skeleton. So we have 1, 2, 3, 4, and 5. Put the numbers here as well. And add the Cl on carbon number 3. So that's going to be the Cl. And also remember, on carbon number 3 you have the methyl, and that's actually what makes that position more reactive, and that's the Markovnikov's position. You do not necessarily have to show the hydrogen. In the first example we have done that just so you can visualize, but as a reference you want to picture this and see that this is where the hydrogen added, that was on position number 4, and that's how we have generated the carbocation in position number 3. And so that'll be the major product, and that's the Markovnikov product again here. Now we're going to do the same thing here. We have the anti-Markovnikov position, and we have the Markovnikov position here. So then in the product, the Br is going to be on the Markovnikov position, and we can simply put a Br here. Once again, so here you need to visualize that this is a CH3 here, while before it was a CH2 on the double bond. So a lot of these things are going to be assumed in organic chemistry too, and it's good to practice this actually without drawing out the hydrogens so you can actually get used to it. Let's do the next one. Here we have the double bond and we have two positions. So this is going to be the more substituted position and this is the less substituted position. And in this case, the iodine is going to end up on the more substituted position of the double bond. So we have the two rings, and now in the middle we're going to have the iodine. Of course, the hydrogen now is on this side. In the last example, so this is a bit trickier, so you need to remember about the rearrangements, and we do actually show the mechanism here. So in the first step, when we do the protonation, we're going to generate two carbocations. So one of them will be this, where we'll put the positive charge here, and the other one is going to be where we put the positive charge here. The thing is, these are both equivalent positions, none of them is more substituted than the other one. And that's why we cannot look at it and directly say that which one is going to be the major product. So here we need to recall about the rearrangement reactions. So remember, the rearrangement reactions will happen if there's a possibility of going from less stable to more stable carbocation. And here, because this is next to the positive charge, this hydrogen can do a hydride shift. It's a 1,2 hydride shift. And by doing that, we'll generate a tertiary carbocation. So this is now plus on the tertiary position. While remember here we had a secondary position, so that's a secondary carbocation. Now I have a tertiary carbocation. And so the Cl then will work as a nucleophile and attack this tertiary position. And we'll end up having the Cl on the top, which we couldn't just expect looking at this because this position is not part of the double bond. So would this still give a product? Yes, it will. Some of this will be generated and some of it will actually react with the chlorine. And it is actually possible to have this product where we have the Cl in this position. In the mixture, you will also find some of the products that are generated from this secondary carbocation. So if you have a Cl present and it attacks before the rearrangement happens, before the hydride shift happens, then you're also going to have this product, Cl on this position as well. Out of this, so most of the time, your instructor, I assume, is going to require you the rearrangement products, but this is something that you may want to check with your instructor as well. So in reality, this is going to be a mixture. You're going to get the rearrangement product and the one that is coming from the secondary carbocations as well.